Okay, so I will I will I will give describe the proofs of the two Liouville theorems I mentioned. So the setup is we first consider this is I will write in n greater or equal than 3 and gamma is a cone. So this is a cone. So we last time we mentioned a theorem. So last time and it says that assume the above and also so this is a special point. So this is in viscosity sense. Then U is constant. So here, this AU, so here, AU, well, I write it in terms of W. So because otherwise it's fairly long. So, so this is n by n identity. Okay. So then this is a theorem. So here, so the fact is, if you add the eigenvalues, by this I mean the eigenvalues of this n by n symmetric matrix. So this is an n by n matrix, symmetric matrix. Hashing is symmetric, identity is symmetric. So if you add that, this is actually identically equal to, if you write out, you will see it's actually equal to minus 2 n minus 2 Laplacian u divided by u n plus 2 over n minus 2. So this is an identity. Okay. So therefore, if you look at that theorem, if we take so if this gamma, you take gamma is gamma 1, it certainly satisfies this. Gamma 1 is not only a cone, it's a half space. So if I draw in 2D, because it's difficult to draw in Hyder, so this is the gamma 1. So gamma 1 is on this side. So which is so then this is gamma 1. So then this boundary gamma 1 is lambda 1 plus lambda n equal to 0. This is the boundary gamma 1. So therefore, when we say this belongs here, then it means Laplacian u equal to 0. So lambda of AU in boundary gamma 1 means Laplacian u equal to 0. So this is positive. So that theorem would say positive harmonic function. In this case, this theorem says positive harmonic function has to be constant. So therefore, this is a nonlinear version of this classical Liouville theorem. Okay, so I did not define viscosity sense. So maybe let me say, let's define what it means by viscosity sense. So, okay. So lambda AU belongs to gamma bar in viscosity sense. So, well, if in classical sense, if you take gamma equal to gamma 1, we are saying this is positive greater or equal than 0. Therefore, Laplacian u is less or equal than 0. So here, in viscosity sense, means this. Let me see. Viscosity sense. Okay. So means this. So this is what it means. For any phi, let's say C2. So phi is less or equal than, greater or equal than, greater or equal than u near a point, and the phi is equal to that U at a point. This will imply lambda of a phi at x bar should belong to gamma bar. Well, so this is a definition of viscous distance. Why one takes such a take a definition in such a way? So, well, if U is C2, you can talk about this by taking two derivatives and then use the expression. You use the expression this. You can calculate and evaluate. You can put, say, at that point, at every point, this lambda of AU is in there. But now we don't have derivative. But suppose U is smooth. If you are in this situation, if U is smooth, you would know that gradient phi x bar equal to gradient U x bar, and the Hessian phi is greater or equal than Hessian U of x bar. So therefore, so I can write down what AU is now. So let me write down what AU is. AU is like this. AU is actually minus 2 and minus 2 U to this power So, so if you look at this expression as a matrix, if U is smooth, in this case, the last two terms will be the same for U and for phi, because this is the same, this is the same. Well, this Hessian of phi is greater than Hessian of U as a unbalanced symmetric matrix. So therefore, this term for phi at x bar will be less or equal than AU of x bar. Okay, so that means your AU is greater or equal than, wait, I put it the wrong order. Give me one. AU, wait. So this way, I put it backward. So what I should do is I should take here less or equal than and that. So therefore, here I should be like this. So this I will be like that. So now we say that so the eigenvalues of a phi will be greater or equal than the eigenvalues of a u. Yeah. So namely this lambda of a phi is equal to lambda of AU plus a mu. So this mu, each mu I will be greater or equal to 0. So mu will belong to gamma m bar. So this part, you know, belongs to gamma. So your condition is gamma plus gamma n belongs to gamma. So gamma plus gamma n belongs to gamma. So therefore, you know this belongs here. So you have that. So namely, if your u is a C2 function satisfying this, then you would have that in the situation. So now, if u is only continuous or u is lower semi-continuous, you can define a super solution this way. So this is a way to define viscosity super solution for lambda AU belongs to gamma bar. So similarly, we can define lambda AU belongs to Rn minus gamma. So what you do is here you have this, then this will be change this to phi greater or equal than that, then change this to belongs to Rn minus gamma, then in that case you call it subsolution. So if lambda of AU belongs to gamma bar and also lambda of AU belongs to Rn minus gamma bar, we say this means lambda of AU belongs to boundary gamma. So this is viscosity solution sense. So I create to prove these theorems for, even though you want to prove this theorem for smooth solution, so you, at least our proof has to go through viscosity solutions. Okay, so next, another property now, another important property for this AU. So this AU is Mobius invariant. Namely, for any Mobius transformation, so by that, it's a finite composition of x goes to x plus x bar, x goes to ax, where a is positive, and x goes to x divided. This is the inversion. So a finite composition of this map. We call it Mobius transformation. Okay. So for any Mobius transformation, and for every function u, we define u phi to be u composed with phi, multiply the Jacobian absolute value 2n over n minus 2. So this is the Jacobian. Jacobian. So AU is conformally Mobius invariant, meaning that if you look at this AU and AU phi and AU composed with phi. So these two n by n symmetric matrix differ by a orthogonal conjugation, or you can say this is equal to that. It's the same. I sometimes put like this. It's the same. So modular permutation, of course. So when I talk about eigenvalues of an n by n symmetric matrix, I do not. I mean the set is the same. So therefore, if this therefore lambda of AU belong to a set, any set, symmetric set, let's say this now, imply lambda of AU phi is also belonging to here. So provided this is symmetric, meaning our definition of symmetric is so lambda 1, lambda n belong to this set implies any permutation and any permutation of all this lambda 1, lambda n, you put, so that's a lambda sigma 1. I don't know how to write it. Yeah, permutation of lambda, lambda I, yeah, still belong to lambda. So this means by symmetric. So from the beginning, when we say this gamma is symmetric, this is what that means. It means if lambda 1, lambda n belong to this set, then a permutation is also there. So therefore, you have this. Yeah. So now we give a proof of theorem 1. So let's call this theorem 1. In the case lambda star does not belong to gamma bar. So the other proof is different. So I will not discuss it here. So the paper is on the archive. So this condition should be understood as certain positivity of this gamma. So roughly speaking, so our gamma, for example, if I put my gamma like this, so if this point is lambda star, so when I say positivity, I mean if you take a gamma like this, it contains eigenvalues of positive definite matrix. So okay, so the matrix is positive definite. So if I open up a little bit like that, so these are not positive definite matrix, but it has certain positivity. It's bigger than eigenvalue, bigger than this function on this side, positivity. So you keep opening up until you include this point. Yeah. So roughly speaking, if you open too much, so you reach some this threshold position, then you don't have enough positivity for a number of things. It's basically for for a number of properties. And that's actually if and only if. So somehow this is so we identify a necessary and sufficient condition on the positivity of this conformal hashing to guarantee a number of properties. For example, this is a condition to remove isolated singularities for super solutions. Yeah, for super solutions. So this is actually necessary insufficient condition. And this property is very important in proving this theorem. Actually, for this statement, that removability of isolated singularity for super solutions is is the new new ingredient in proving this. Yeah. So, but I will describe the proof, including previously known ingredients. So, okay. So how to prove this? So we are going to prove the following property for function u. So, for every x in Rn, and for every lambda positive, sorry for abuse in notation. So this is actually a number. I'm used to use lambda as a radius of a ball. So I will just, so I don't change it because so this way I don't have to really look at my notes. Yeah. So this is lambda. So this is a ball. This is a ball with radius lambda and centered here. So with respect to this ball, there's one Mobius transformation. It makes the inside out and outside into it. So this is, I use notation phi x lambda. So it maps y to x plus lambda square y minus x divided by y minus x square. Okay. So this is the transformation, this inversion. Whenever you have a point, say here, so where is you map it to phi of, you map it to here. So what you do is what the map does is this. You go from here, you go through y. It's always on this ray. So it will be mapped to here. So if I now call it z, so this point, z minus x times y minus x y minus x should be equal to lambda square. So this relation determines the map. So first, z minus x, if you see, you will see that immediately. And this is exactly how this map goes. So the map only map this y on a point on the ray. So it's always on this ray. And this distance determines where it is. So of course, if it is on the boundary, so you see, if y minus s is equal to lambda, z minus x is also equal to lambda. So it doesn't move. Okay, so it doesn't move. So, and it maps inside out, outside in. Okay. So we know, okay, so we are going to, okay. So we will prove this u, you want to prove u is constant. U satisfies an equation. A lambda of AU belongs to boundary of gamma. So it satisfies that equation. So you want to prove for that u, it has the following property. Or you simply write u phi x lambda greater or equal to u in b lambda x minus x. So you want to prove this. So actually, once you can prove this for every lambda and every x, so you prove this for every ball in the Euclidean space, this will imply u is a constant. So this will imply it is a constant. So what I'm saying is this function u has this property. For every x and for every lambda, you have this in the puncture ball. So then it's a constant. And in fact, so this one, you can write it out. So this is actually is equal to lambda over y minus x n minus 2 u of x plus lambda square y minus x square. So this is exactly this part is phi of x lambda y. Okay. And this part is the Jacobian, comes from the Jacobian. The Jacobian, yeah. Okay. So why is this? Why it implies that? Okay. So the reason is, so this reason is this. Reason for this part. So yeah. So let's say this is origin and this is an axis. Yeah. So if you pick any situation like this, we are going to prove. So we are going to prove that this point, okay, you take this as a point. So if I take, for example, if I take a very large ball like this, and if I take a very large ball centered here, so this y is fixed, y is fixed. You fix your y fixed. So x is moving towards towards here. Okay. So this radius is exactly with the radius, it make it touched here. So then you know that this point, there's a point So this point is the point Z. Let's call it a phi x lambda at y. So this is the symmetric point with of y with respect to this sphere. Radius is this, center is that. So this is the symmetric point here. So you know that u phi x lambda should be greater or equal than u of y here. So this actually tells you the value of u of z, the symmetry is greater or equal than that. There's the Jacobian, of course. So what I'm saying is then we have the formula. If you write down the formula here, now I send your x to here. So then this sphere become bigger and bigger, and this y will approach to y star. So this is a symmetric point of that, because when this goes to this side, this point will go down to here. So then your limit, you can write that formula, you can write this formula, so this is x absolute value. So then you will end up with uy star will be greater or equal than u of y by doing that. So this means your function u is on the left is greater or equal than the right. Okay. Well, I create you can put this argument to get any 2 points. Left will be greater or equal to right. You can change, you can rotate your axis to fit into what I'm describing. You already prove u is a constant because any 2 points, you do it this way. You take any 2 points, you call it y star and y, then you select your 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 axis like this, then you do your process, you will get this. So that means u is constant. So it's just a simple consequence of that. So therefore we want to prove this. Okay. So why do we have that? So and when we go through the proof, you should think of the uh, uh, harmonic function actually. So first, so now I know that I have a punctured ball here, radius. So this is a punctured ball. In this punctured ball, I know this u phi x lambda, okay, this AU, it belongs to boundary gamma. And we know that. We also know that lambda of AU satisfy the same equation in the whole ball. So here the important thing is one can prove. So this is really the key now. So one can prove this lambda of AU phi is actually a super solution in the whole ball. So here one uses this lambda star does not belong to gamma bar. Okay. If lambda star belong to gamma bar, they will be there is actually smooth super solution, uh, uh, which which is not, which cannot be extended across. So I'm not proving this now. So I hope at some point I can prove some, I can describe at least how this proof goes and so on. Okay. So this is something I'm not doing. So, but you can think of this as when gamma equal to gamma 1, what we are saying here, if this, we are saying super solution in B lambda x minus x bar x, and we are going to Laplacian u less or equal to 0 in B lambda of x. So remember that, recall that we have this condition. Okay. So this is true for superharmonic function. If superharmonic positive, then super solution in punctable will be extended in the whole ball. So here we proved such a property for our equation. And now we know that this u phi x lambda and u is the same on the boundary. Yeah. So this is just from the, because this inversion is not, is an identity on the boundary, and our expression will tell you this. So we have now two things. So first, we have this, a super solution in the ball. Now we have a subsolution in the ball, and they agree on the boundary. So here we use a comparison theorem. So this was proved before our new work also. And then you know that u phi x lambda will be greater or equal than u in B lambda of x. So this is the proof for the Liouville theorem when lambda star does not belong to gamma bar. So this proof uses very heavily conformal invariance. So one question would be, so if you change this operator a little bit, perturb it a little bit so that conformal invariance is violated, are there still such Liouville theorems? Or this conformally invariant operator is absolutely crucial. So there should still be, there's still a need to understand this further. So how how general this Liouville theorem should be. Yeah. Yeah. Okay. Okay. So I will also uh, describe another theorem. So this is the second theorem I mentioned last time. So this is an extension of the classical Liouville type theorem of Caffarelli, Gidas, and Sprague to a nonlinear situation. So again, we have this gamma So we look at this gamma. And now the condition is does not belong to gamma bar. So this is the positivity we set. So this gamma has this positivity. And actually, this is a borderline. This is optimal positivity for the theorem to hold. So you can roughly, you are writing a cone, somehow writing a cone like, so it can go over this gamma 1 actually, and this lambda star is here. Yeah, so you can say this is gamma. Okay. So in this case, if there's a, so let f be a function symmetric. Symmetric means f of lambda is equal to f of lambda hat if lambda hat is a permutation of this lambda. Okay, that's the, so df, okay, this is ellipticity. Yeah. So assume that, so we have a C2 function. It's a C2 function. Every point, let's look at classical solution of so this is the equation. Then this U will have to be of a specific form. And actually this AB should not be arbitrary. This AB is not, because this, the fact is for this function U, this AU star, let me see. So for this U, the fact is this U, I don't remember the specific form. For this U, lambda, this AU is exactly equal to, I don't quite remember, maybe it's -2, B, I don't quite remember, identity. So it's a number like this. Okay, I don't quite remember. So it's some number. So therefore, your equation will tell you f of a minus 2b, a minus 2b has to be equal to 1. So this is completely fixed. There's only one such number, actually, because this is... Anyway, so this is the theorem. Yeah, this is the theorem. So the theorem, actually this f, when we talk about f, actually we really talk about f equal to 1. So we are saying the eigenvalue is lying on a hypersurface. Okay, this is what we are saying. So, or if I draw a gamma like this, if I draw a gamma like that, this is gamma. And if I draw a hypersurface like this, if I draw a hypersurface with inner normal belongs to Rn, a gamma m. So each component of the normal points to the first quadrant. So then you can always put an f so that df d lambda I positive. You can even put an f which is one homogeneous in this case. I mean, well, anyway, you can easily put the function f. So your theorem is actually the same as you put a hypersurface like this, then eigenvalues of this conformal question lies on that hypersurface. The requirement for the hypersurface is this inner normal should point to the positive cone. So it's very easy to draw such hypersurface. So namely, there's a lot of f. F is actually in this theorem just occurs like a hypersurface. It's the same at this condition. So I will so for so I will go through this proof and I will point out where are the important new new ingredients for us to prove this theorem. So, but I will also describe the previously known procedure. So we prove this by the method of moving spheres. Then I will point out which part are the new ingredients we find out, and later I will find time to describe part of those new ingredients. Uh, any questions? Please interrupt me. There should be a way to ask me questions. Yeah. Let me see whether I don't know where I can find questions. Right. Okay, so I don't know if you have, there's a question. Is there a way to ask questions? Yeah. Okay. Okay. So no questions yet. Okay. Okay. Huh? Here's something. Ah, I see. Ah, chat. There are some questions. Okay, very good. Okay. Is there, so here is a question. Is there always a unique cone gamma satisfying our given condition in Rn? If not, then does the theorem imply that it suffices to find one cone satisfied conditions of the theorem for given U to prove that U is constant? Is there always a unique cone gamma satisfying? Okay. Uh, so for theorem one, it's like this. So for theorem one, Okay, what does theorem say? Theorem one says that there's a set. So now happens to be in my description, this is a set in Rn. This set is specific. So it has to be the boundary of this cone. So this is the set. So of course you can draw such a set very easily to satisfy your condition. Your gamma is a symmetric cone, gamma plus gamma n is in gamma. So this condition meaning that if you translate your gamma n to every point in your gamma, so let's say this is gamma. If this is side is gamma, at every point in the gamma, if you translate the first quadrant here, that should still be inside gamma. Okay, so you can very easily draw such set. So then the first theorem says that if you give me a function and you tell me lambda au actually belongs to here, okay, at every point in Rn. This function has this property. So it's a property for the conformal Hessian. So that implies u must be constant. So note that if u is a constant, for u is constant, au is actually equal to the origin. Because the au, you look at the expression of au, it involves derivatives of u. So it's just a zero. So meaning that this lambda au for your constant function is actually always here. Okay. Okay. So for the second theorem, what it says is is in Rn. If you start from you can equivalent to state like the following. You can start with any surface. You give a surface like this. You call it sigma. So the normal hypersurface belongs to gamma n. So this sigma, you put it on this side. So then this sigma will generate a cone. You call it this gamma. Okay. So in this picture, this will be your generator. Well, you will generate a cone. You will generate a cone. You will generate a cone. Something like this. This will generate a cone. Yeah. So that this sigma, so this will be a gamma, sigma will be strictly inside. So if this gamma, the cone you generated, satisfy your condition, okay, it's not. So then, if you know lambda of au belongs to this sigma in Rn, at every point in Rn, you calculate this au, you look at the eigenvalues, they lie on this hypersurface. Then the conclusion is your u will be identically equal to that specific form. So this is the theorem. I should say then for this u, your au lambda is actually, so I do not write, so it's a very specific, maybe like -2 and b square, or there's a constant somewhere for this number, times 1, 1, and 1. And this is a positive number, specific. So namely, so in fact, even you assume your eigenvalue is in here, but actually then you prove at the end of the day, you prove that this is the one one multiplied by C positive, this ray. Okay. You show that actually the it has to be here. So the lambda of AU has to be there. So this is at the end of the day, you prove it has to be here. But you a priori you assume it's like that. So it has to be there. Okay, so this is the theorem. I don't know whether it answers this question. More or less, I think I'm saying things around this question. Yeah. Okay. So now I will give a proof of this. Proof of theorem 2. So step 1, I will prove that for every x in the space, there is a small number this is small, such that small, fixed. So let's not to put this. What I mean is small. So less than 1. Yeah. It's a small number such that for all lambda less than this. So I look at sphere centered at x with radius lambda. So namely, if radius of sphere small enough, I know that u x lambda. So this originally I wrote it as u phi x lambda, but I just write it like this, so it's easier. So this will be greater or equal than u of y for every y belongs to b lambda x minus x. I want to prove this. So namely, the reflection is above the function u inside the puncture ball. Okay. So maybe, so because I only have 8 minutes now, so let's keep describing the strategy. I will then prove the uh, give details next time. So I will first prove this. So this is like moving sphere procedure. You can start. Okay. So for this procedure, I'm going to use the following property. So for this, for function u to have this property, the following will be sufficient. So the following will be sufficient. One is 0 less than u, and this is C01 log of Rn. Okay. And if I know y n minus 2 u of y lim inf y goes to infinity is positive. So namely, if any function u with this property, we are going to achieve the first step. So for us, the first one is okay. So we only look at this solution. Actually, we look at C2 positive solution. It's more than enough. But for this, is we need to prove it. And actually, this is for this, we used lambda star belongs to gamma bar, doesn't, and lambda of AU belongs to gamma bar. We use this property. So to have this property, we have this. So to have this, we need this conformal Hessian have enough positivity. So in fact, this is actually necessary as well. In the sense, if lambda star is in the gamma bar, namely this gamma does not have the threshold, this positivity, then there will be a positive function, smooth u, satisfy this, satisfy that, but does not satisfy this. Okay. And if this is not satisfied, if you cannot guarantee this, so you see the moving sphere procedure can work, imply you have this, because this condition imply that. So in a way that you have to have a way to prove this property for what if you want to use moving sphere, right? Yeah. So here we say this is enough. And so this is an important new ingredient. So in the past, we know if gamma belongs to gamma 1, for example, if you look at Caffarelli-Gitas-Sprach theorem, so that minus Laplacian u is equal to u to some power. So this is positive. So Laplacian u is actually less than 0. Therefore, so if lambda au, actually also whenever you have this, you will have Laplacian u less than 0. So if you have Laplacian u equal to 0, this is very easy. This is maximum principle. Because u is superharmonic, u is positive, then at infinity you compare to harmonic function like this. Okay? So you will immediately see this just by standard property. For example, if you start, you work on that. So in fact, the theorem for gamma belongs to gamma 1, it was known before. It was previously proved. So what we are doing now is for gamma going beyond that. So for example, even for the first step, one has to do some serious work. Okay. And also we have identified this optimal condition to guarantee all this. Okay. So this is the first step. So as usual, once for the method of moving sphere, once you prove this first step, you will define, you can define lambda bar x to be the supremum of those radius. Okay, so you have this property. The property is the reflection, the Kelvin transform is greater or equal than u of y for any y belongs to b lambda x minus x. So this is a property with radius. So this is true for any radius here. So then you take the supremum. You push this property to the maximum. So of course, this is less or equal than infinity, but you know actually it is actually positive by step 1 because we after establishing step 1. So this number is going to be 0, so either finite or infinity. So an important second step is if lambda bar x is finite for some x in Rn, we have u x lambda bar x will be identically equal to u. So you can say in B in Rn minus x because that's a singular point at x. You will have this. So this is an important step. So in this movement method of moving sphere, so this is the main PDE step. So after this step, once you establish this, so for our new ingredient, we need to establish this step for under our condition, under lambda star does not belong to gamma bar, so lambda of AU belongs to gamma. So we establish, we use this property. Yeah. So again, if gamma belongs to gamma 1, so we certainly satisfy this. So our result was known before. So our main thing in this new work is to identify this threshold positivity. Yeah. And once you establish that, it will be known that either ux lambda bar x, either lambda bar x finite for all x in Rn, or lambda bar of x identically equal to infinity for every x in Rn. So you can prove very easily once you prove step 2 and 1. So this would imply u is a constant. So this property, so this means, because this simply means ux lambda is greater or equal than u in this punctured ball for every lambda positive, for every x in Rn. This is what we are saying. So this property implies u is constant. So this property would imply ux lambda bar x identically equal to u in Rn minus x. So this is step 2. Any function satisfying this, okay, you don't need any PDE, any function satisfying that would imply u is of that form. U is of this form. So that property would imply this u is of this specific form. So, okay. So then we finish the proof. So so next time I will carry out the details of this and will describe how those key properties are proved, at least give some discussions on those. Any questions?
Any questions?
Pardon?
Any questions online?
Pardon? Yeah. You can ask questions I can probably hear maybe. And
Any questions online? Okay, looks there are no other questions right now.
okay.
And
So I will continue tomorrow, right? Yeah. Mm.
thank you. Yeah.
Okay.